Hello. So these are some solutions to a few additional problems that you might use for your final studying for tonight's midterm. So question 31 is asking us to pull some information from Appendix C that's, you know, sometimes I attach it to activities, but if it's attached, it's like the appendix you can look up in the end matter in the back of the textbook that lists all the delta HF values for a bunch of compounds. And here we would just be taking the sum of the products. So we'd take like 8 times the delta HF of CO2 plus a 9 times the delta HF of water. Technically, it's 8 moles, 9 moles. So we take kJ per mole values. Um, and so the delta HFs are in units of kJ per mole. So we multiply by the moles. And then we would subtract 1 mole times the delta HF of C8H18. The delta HF of oxygen is 0 by definition. So we don't need to account for the 25 halves O2. And all of this equals minus 5471 kJ since we're given this information here. And then we would just be looking this up here, taking into account the particular phases, and then solving for the delta HF of C8H18. We did a problem like this. I think it was the very first problem we did this Monday in lecture if you want a similar problem. So we're just going to leave it at that here. 32, we're also would be looking up these delta HF values. So we'd be taking, CCl4 plus 2 times 0. So we get a delta HF of 0 for H2. The same for chlorine because those are elements in their standard state. And then we'd look up the delta HF of CH4. You can imply that it's exothermic because all the choices are exothermic, but we'd just be taking the delta HF of your product minus the sum of the delta HFs of the reactants. So products minus reactants. Now, I deleted a problem from the next page. The next page is getting at, from the magnitude of delta H, they're all negative. So this reaction is exothermic. The reaction is exothermic because we're forming stronger bonds in the products than we are the reactants. So if you look at your reactants, enthalpy, we're losing enthalpy down to the products. This negative delta H, that's why we're going downhill. We're forming more stable products because their bond strengths are stronger. So exothermic reactions, products bonds are stronger than the reactants, and then endothermic reaction, the reactants bonds are stronger than the products. Breaking a bond is always endothermic. Making a bond is always exothermic. So we have the input energy to break a bond. We get energy back when we make a new bond. The question is, are the new bonds stronger collectively than the bonds we had to break to get there? So if you use a bond enthalpy chart, remember your delta H is an approximation with the bond enthalpy chart, but it's approximated from the sum of the bond strengths, break the bonds in the reactants, minus the sum of the bond strengths of the products. There's an example of that in a couple of slides. Okay, so these were some problems we skipped over, 19 and 20. So potassium hydrogen phthalate, KHP, is a solid monoprotic acid readily available in pure form. And so the reason why this solid's used is you can put it in an oven, dry off all the water so it's nice and pure. And you can then dissolve it in some water, and then you can titrate it with a solution of base. You dissolve it, add a little bit of pH indicator, and then so you can titrate this with the base. If it takes 25.50 mils of a stock solution of KOH um, to titrate 0.6575 grams of the acid, what is the molarity of the KOH in the stock solution? This is how you determine the KOH concentration that you might titrate something with later. And so the way we can go about here, since this is monoprotic, KHP reacts with KOH to form K2P plus H2O. So think of this as like the hydrogen phosphate anion here So we kick off the H and we go to a 2 minus. We have 2 potassium. So if you think of this as like potassium hydrogen carbonate, for example, then we're just going to CO3 2 minus. So we're just going to the from hydrogen phthalate to the phthalate ion here. So we need 2K pluses to balance it. All potassiums are AQs, liquid. The key is monoprotic, so 1 KOH is needed for every 1 KHP. Now what we can work out is from the given mass here, we know how many moles of acid there were. So we can determine the concentration of KOH that we're titrating with. What I would do is I would say, well, how many moles of KOH were present in that solution divided by the volume of that solution would be its molarity. And I calculate the moles of KOH by taking the moles of the acid. I get the moles of the acid starting 0.6575 grams times 204.22 grams per mole of KHP. For every 1 mole of KHP, we have to add 1 mole of KOH. And that's my moles of KOH. So what we're basically saying here is that we started the titration with 0.6575 divided by 204.22. So we have 0.003219.5, etc. moles of KHP. So we have to add 0.03219.5. So 0.3220 moles of KOH. So for every mole of KHP, we have to add a mole of KOH. And so once we see that color change, we know that's the moment that that portion of KOH at 25.50 milliliters had contained this number of moles of KOH. And so then we take this molarity here, and then we divide it by the volume to go to our concentration. So by 0.02550 liters. So it's expressing 25.5 mils in liters. I get 0.1263 molar. Answer C. So this is how you determine the concentration of something like KOH from a titration where you start with a solid organic acid, monoprotic, we're told. We know the formula. We can even think about how a hydrogen phthalate is like hydrogen carbonate. So you see H phthalate. So you're just removing the H, going to an extra charge, adding a second potassium to balance it out to write our reaction, our monoprotic acid-base reaction. 20, which methods can be used to determine the concentration of HCl in a 10 ml aqueous solution of HCl. Determine the volume of sodium hydroxide required to titrate the solution. So if you know you have 0.1 mole of sodium hydroxide, see how much volume it takes, you have to add some indicator to see it, so that works. And then add an excess of silver nitrate. This should work because HCl should react with AgNO3 to produce a precipitate AgCl, solid plus HNO3, water soluble, doesn't precipitate. You can take this precipitate, filter it off, so add an excess of silver nitrate, cause the formation of precipitate, and determine the mass of that dried precipitate. So decant the liquid, and then dry it off, and then, so both of these methods should work for determining. The reason why both these methods work is you can determine from the moles of AgCl how many moles of HCl there were. From the moles of HCl, you can divide that by the volume to get its concentration. Same thing with seeing how much sodium hydroxide it takes to react with it. 6, I got this question a couple times, so I'm going to throw this in here. This is on some practice exam too. I think chapter 6, review number 1. The ionization of sodium is 496 kJ per mole. In an experiment similar to Hertz, which Einstein famously explained the photoelectric effect, which statement below would be true for this type of radiation that could cause sodium to be ionized? So if sodium absorbs 496 kJ per mole, it can lose an electron and become ionized to sodium plus. The question is, how much energy does it take for 1 sodium to become ionized? Well, that would be 496 kJs per mole of sodium. 1 mole of sodium is 6.022 times 10 to the 23 sodium atoms. And then a kJ is 1,000 joules. Now, why do we want this in joules? Well, I'm going to try to then take photon of light, the energy of a photon, where one photon can interact with one atom. And then this can go to the atom plus the electron, that if the energy of the photon is high enough, it can cause that atom to become ionized. And so E is equal to h nu equal to hc divided by lambda. So if I'm going to find the wavelength associated with the energy it takes to cause the atom to be ionized, I'm thinking one photon, one atom. So one atom of sodium requires 496 divided by 6.022 times 10 to the 23 times 1,000. That's 8.236 times 10 to the minus 19 joules. And so my photon energy, which is equal to hc divided by lambda, because I want to find the wavelength here, that if this energy is greater than or equal to 8.236 times 10 to the minus 19 joules, then we should be able to have the atom ionized. And so if I do my cross multiplication, put lambda over here, you see how now I want my lambda to be less than or equal to hc divided by this energy here, 8.2, what did I write? 8.236 times 10 to the minus 19 joules. And so then if I do this math here, so if I take 6.626 times 10 to the minus 34 joules times seconds times 2.998 times 10 to the 8 meters per second. There goes the per seconds canceling with the seconds and joules times seconds. Divide by 8.236 times 10 to the minus 19 joules. There goes the joules. I get my wavelength here in units of meters. Whoops, flip my sign here. I want my wavelength to be less than or equal to this value here. Let's come back to y less than or equal to in a minute as well. So I do 6.626 times 10 to the minus 34 times 2.998 times 10 to the 8, divide by that energy, and I get 2.41 times 10 to the minus 7 meters, 1 meter, 10 to the 9 nanometers. So I do times 1 E9, 10 to the 9, that's 241 nanometers. So I want my wavelength of light to be less than 241 nanometers. Now, let's come back to why we want to be lower than 241. So think about E is equal to hc divided by lambda. So lambda of 241 is the precise amount of energy to cause sodium to be ionized. Now, if we go to a longer wavelength, we're dividing hc by a bigger number. That gives us a lower amount of energy. So if we go to a longer wavelength than 241 nanometers, then we don't have enough energy to cause sodium to be ionized because that's going to a smaller energy. But if I go to a lower wavelength, if I decrease the wavelength from 241, then I go to a greater energy, which allows sodium to have enough energy with that photon hitting it to become ionized. And so one photon can interact with one atom to cause, or one molecule to cause one event to take place, in this case, one ionization of that electron. And so as long as we're lower than 241, we can cause that ionization to take place. And so it's the 496 nanometers here is just kind of a trick answer because the 496 kJs per mole isn't the nanometers. We have to think energy of the atom to one atom to the energy of the photon, and then from there calculate the wavelength of the photon. Something about state functions, I get this question a lot. What is a state function? A state function is a path independent function. And so like A goes to C, delta H is equal to, say, or let's keep it delta E. But delta E, delta H are state functions, meaning it doesn't matter how we get from A to B, they're the same, or A to C in this case. So the delta E here, let's say this is minus 20 kJs. If we go from A to B, from B to C, we know that if you take the delta E's and add them up, the A to C, that this still has to come out for a two-step reaction to have the same delta E. So we have to get the same delta E for these steps, regardless if it's a one-step reaction or if we do like a two-step reaction. We have to get the same delta E because delta E is a state function. Now, if you imagine, maybe when we carry A to C out, we carry it out in some sort of vessel where there's no work. So let's say W is equal to 0 in this case here, then Q is equal to minus 20 kJs if we carry out the reaction directly from A to C. Now imagine that you go from A to B and the delta E here, let's say, is minus 10 kJ still, and then delta E for the second step is minus 10 kJ, just hypothetically. They add up to minus 20 as they should. But then let's say for some reason we carry this two-step reaction out, and then the second way we carry it out, Q is equal to minus 5 and W is equal to minus 5. And so kJs each. And so those Q plus W still sum up to minus 10. And then if I take reaction 2, and let's say it's the same thing, where I carry this out, I get minus 5 kJs, and I get W is minus 5. So I'm using the energy from A to B and B to C to do some work. And I'm carrying these reactions out in a different type of container or vessel or some way that allows me to have this reaction do a lot of work as opposed to just generating heat. And so then when we get to the final kind of like A to C, we're noticing that, okay, we got minus 10 kilojoules of heat out of this reaction, but we got minus 10 kilojoules of work out of this reaction. The sum of Q plus W is equal to delta E. So the sum of Q and W still go to minus 20 as they should, but you can see that Q and W depend on the pathway that we're carrying these reactions out. So Q and W depend on how the reactions are going in terms of what their values can be. So we do the reaction this way, from A to C, we get minus 10 kJs of heat, minus 10 kJs of work, but we carry it out some other way, we get no work, minus 20 kilojoules of heat. And so work and heat are not state functions. They depend on how we're carrying these reactions out, so these are not state functions. The only thing then that becomes a little confusing is, well, what are state functions? So like, um, um, so work and heat, not state functions. Heat's not a state function. Enthalpy is. So delta H is a state function like delta E. And like that helps you know that if you flip a reaction, you flip delta E. If you flip a reaction, you flip its delta H as well. So delta H and delta E are state functions, so they're path independent. The sum of heat and work is a state function, so heat and work can't just be anything. They have to sum together to be delta E. Internal energy, E, and enthalpy, these are both state functions. And then pressure is a weird choice. I just don't like this as a choice. This is from some other exam. So I think pressure is a little tricky to understand, but pressure wouldn't be a state function because it's kind of related to how much gas just happens to be present from the reactant product. So we could generate a gas, increase pressure. We can consume a gas, decrease pressure. If we have an open system, then we can't really change pressure at all. So pressure depends on how we're carrying the reaction out. It's a little bit of a tricky question. I don't think we'd put this into a choice, but pressure is not a state function. So here's a bond enthalpy question, kind of going in and out of some different concepts. So the bond enthalpies, we're breaking our bonds, and then we're making our new bonds. Now, we can be clever and notice that we're only actually breaking one of the CH bonds. So we're really just breaking one CH, and then we're breaking the Cl2 bond, 242. These are kJs per mole, and then times 1 mole of that bond. And so this is the sum of the energy it takes to break the bonds. So that makes my fragments. So that breaks this into 2 chlorines. That breaks this into a CH3 plus H. And then we just simply pair these together. We take an H and a Cl, make a bond, and we take a Cl and pair it with the chlorine and make a bond. So we're making this bond here, and then this bond here. So a carbon chlorine is 328 kJs per mole. we're making 1 mole of that bond. Cancel, and then we're adding the sum of the other bond. We make the HCl bond is 431 kJs per mole times 1 mole. So sum of the enthalpies it takes to break the bonds in the reactants. So that's going to be 413 plus 232, or excuse me, 242. And so it takes 655 kilojoules of energy. So if we go from CH4 plus Cl2 to CH3 plus H plus 2Cl, this takes plus 655 kJs. And then when we think about going from CH4, or excuse me, CH3Cl plus HCl, if we imagine breaking the carbon-chlorine bond, the hydrogen-chlorine bond, the 328 plus the 431, we're breaking these back into these fragments like this. Excuse me, this would be plus Cl plus H plus Cl, so that's Cl2, so 2 chlorines plus an H. And that's so breaking this bond here and this bond here takes 328 plus 431, takes 759, but I had to, making the bonds now flips the reaction. So instead of breaking the bonds, I'm making them. So I have flipped the breaking of the bonds equation, so that's why this is minus 759 kJ. So the minus here comes from the fact that we are flipping the reaction to make the bonds using the bond strength chart. And so we're making the new bonds, so the bonds are the products, the fragments are the reactants, and so that's why the minus sign is here. This is why it's the sum of the bonds to break the bonds in the reactants minus the sum of the bonds in the products. So the delta H we get as an approximation here, sum of the bonds of the reactants minus the sum of the bond enthalpies of the products. So 655 minus 759 is 104 minus 104 kJs. Okay, so this is just a consequence of kind of how Hess's law works, or the idea how much heat does it take to break the bonds, how much heat do we get back when we make the new bonds. Because this goes negative, the new bonds are stronger. So the new bonds are stronger by 104 kJs than the bonds we had to break. Now, one thing I wanted to say is if you were like, well, what if I broke all 4 here? Can I do this and just break all the bonds? We could do that. So that would be times this way in a color. So we could have had this instead as 4 moles being broken. And then we would have had this here as 413 kJs times 3 moles being made for the 3 CH bonds that we didn't consider here. So if you notice, we added 413 times 3 from what was here before, and then we just added over here, and we're subtracting that energy anyways. So if you want to break all the bonds in the reactants, you can do that. You just have to then make sure you make all the bonds in the products. And if you do like 413 times 4 plus 242 minus 328 times 4 minus 431, 413 times 4 plus 242 minus 328 minus 413 times 3 minus 431 is still equal to minus 104. So that gives us the same minus 104. So I have a sulfuric acid solution being titrated with 1.95 molar KOH. What is the concentration of battery acid? And so in this problem here, my concentration of H2SO4 is going to be equal to the moles of H2SO4 divided by the volume of that solution. The volume of the solution of the acid is 25 mils. And then the moles of H2SO4 I get from how much KOH it took to react with it. So I get 1.95 moles per liter of KOH. And then I use 0.08742 liters of that solution. And then times for every 2 moles of KOH we had to add means that there was 1 mole of H2SO4 present. So I've gone from moles per liter times liters to moles of KOH to now converting to moles of H2SO4 that are present. And so 1.95 times 0.08742 divided by 2 is 0.085223 moles of H2SO4. Now, if I divide this by the volume of the H2SO4 solution, I get 3.41 molar. That's doing the 0.08523 moles of H2SO4 that were initially present in the solution, and then we're dividing by 0.02500 liters. This is my concentration of H2SO4, before we start that titration. We do the titration to figure it out. That's the whole point of it. One of the keys in this problem here is if you do M1V1 equals N2V2, it's not going to work. And it's not going to work because that equation has nothing to do with this problem. So if we're solving a stoichiometry problem, you have to have a mole-to-mole conversion somewhere in the problem. It's right here. Okay. Molar concentration of ions in 2 molar iron chloride. So this is water soluble. Like you can kind of imply that from it being moles per liter in solution. And so for every mole, so the M is moles of iron chloride per liter of the solution. For every 1 mole of iron chloride, we get 2 moles of Cl minus, so the concentration of chloride ions is 4 molar. Oxidation number of chromium here, we got 2 plus for calcium based on the periodic table, minus 2 for oxygen for the same reason, minus 14, 7 times minus 2, plus 2 for calcium. And so calcium plus 2. So what do the 2 chromiums have to be to sum up to the overall charge? There's no charge indicated here, so this is 0. So sum to 0. So plus 2 plus 12 for the 2 chromiums. 2 chromiums divide out that plus 12, so plus 6 each. So the oxidation number of chromium is plus 6. So again, 6 plus. So we go 2 plus 12 minus 14 equals 0 as our check. Helium gas shown here. What is the sign of work for the gas? So we have the surroundings is decreasing the volume of this container. So we have the piston moving inward. And so is that the system of helium working on the surroundings, or is that the surroundings working on the system? This is the surroundings working on the system. And I like to think of this the same way as the surroundings heating up, like giving heat to the system. So if the surroundings heats up the solution, so the surroundings pushing into the system, that's the same as if you imagine heat flowing from the surroundings into the reaction. So if heat goes into the system from the surroundings, so the system absorbing heat would be delta H being endothermic. So if heat's coming inward, delta H for our system less than 0. Q less than 0, the heat is absorbed by the system. Here, work is being done with the same sign. So the idea here is if you have a piston coming inward, that's the system having work done on it by the surroundings, the same thing as the surrounding heating up the system. And so I'm just trying to draw the analogy to heat flowing inward, work flowing inward. Those have the same sign of positive. If you imagine the opposite, if you imagine this system here expanding, then that's the system pushing into the surroundings, that W would be less than 0, and then Q, if heat's flowing from the system to the surroundings, would be less than 0. So try to think about how, what physically would it mean for Q to have a sign of negative, and think about the same implication for W having the same sign. So heat flowing out of a reaction, exothermic, work pushing outward, expansion pushing outward would be negative, and then contraction and then heat contracting inward as well has the same sign as each other as being positive. And so this would be, so the answer to the question here, what is the sign of work from the piston coming downward onto the system, is that the value is greater than 0, so work should be positive because work is done on the helium by the surroundings. If the system does the work, so if helium is working on its surroundings and the helium is pushing the surroundings out of the way. So the expansion, so the statement, helium, work is done by helium on the surroundings. This statement here is the definition of expansion, and this would be W being less than 0 and negative. Last question, which of the following transitions of the H atom would emit a photon with the longest wavelength? So longest wavelength is, of course, a transition that has the lowest energy. And then emission is high N to low N. Is emission, absorption is low N to high N. So we're looking for high N to low N. So 4 to 3, not 4 to 5, that's absorption. 1 to 2 would be absorption of energy. 4 to 1. So we have 4 to 3, to 2, all the way to 1. So 4 to 1 is going to be the greatest energy. 4 to 3 will be a lower energy. So the longer wavelength is for 4 to 3. Now, if we were asked to calculate the wavelength associated with one of these transitions, we could say, well, what's the wavelength associated with the emission from 4 to 1? How do we do that? Well, the equation I would use is the Bohr model equation. Energy is a function of N is equal to minus 2.1. The book in the exam chart rounded to 8, 2.18 times 10 to the minus 18 joules times 1 over the N value squared. I like to use 2.179 to get an extra sig big, but minus 2.18 times 10 to the minus 18 joules 1 over N squared. What we would do is we would calculate how much energy does hydrogen lose from 4 to 1, and that's the energy gained by the photon. Kind of like a system surroundings problem. There's an equation that looks like this: 1 over lambda is equal to some Rydberg constant. I don't even know the Rydberg constant. I don't like that equation. I don't care how you solve a problem, but the way I would solve this problem, the way I think through this is I take the energy of my final state of 1 minus my energy state of my initial state of 4 to calculate my delta E. This is for the H atom. So I can calculate the energy that the H atom changes here, and this should be a loss of energy for my final minus my initial, or excuse me, my final minus the initial. So we're initially in 4, going down to 1, so final minus initial. So I'm just plugging in a 1 here, so I do minus 2.18 times 10 to the minus 18 joules times 1 over 1 squared, and then minus negative 2.18 times 10 to the minus 18 joules times 1 over 4, 1 over 4 squared. Do negative 2, and it's on a negative sign, so just plug in and do the math the right way. Negative 2.18 times 10 to the minus 18 joules minus negative 2.18 times 10 to the minus 18 joules divided by 16. Now this should be negative, as mentioned earlier, it should be negative. The H atom is losing energy, 2.04 times 10 to the minus 18 joules. So H atom loses energy. Where does energy go? It's gained by a photon. So the energy of the photon that it gains is equal to the negative the energy of the H atom. Like a system surroundings problem. The photon becomes our, goes off into the surroundings. The H atom was our system. So the energy lost by the atom given to the photon. And so my photon energy, of course, is just plus 2.04 times 10 to the minus 10 to the minus 18. 10 to the minus 18 joules. Let me zoom in, it makes this font super big. But what I want to do here then is take this energy here and make this equal E is equal to hc divided by lambda. And to solve for lambda. So 6.626 times 10 to the minus 34 times 2.998 times 10 to the 8, divide by that energy. And then that gives me 97 nanometers. So it's 9.7 times 10 to the minus 8 meters, 1 meter, 10 to the 9 nanometers. So I'm just multiplying by 1e9. That's 97.2 nanometers. So that's an ultraviolet photon. I think we should predict this would have been ultraviolet. Oh yeah, this wasn't like a problem. This was, just me asking this extra question. So the wavelength we would calculate here, 97.2 nanometers for the n equals 4 to 1 transition. This is in the UV region of the electromagnetic spectrum. The 4 to 3, you can think here, if you know 4 to 2 is visible, 4 to 3 is not invisible, it's going to be in the lower energy. This is in the IR region. So the lower energy form, the UV is in the higher energy side. Then our visible peak from 4 to 2. So that's all the problems I kind of had planned to review in class. So hence the extra video of some problems here. Again, good luck on the test tonight. And I have office hours today for anybody watching this before 1:30. So 1:30 to 2:30 in 2047 McPherson. Take care. See you guys on Friday.